All right. Well, hello. Today's video is all about making something called standard solutions, solutions of known concentration, and dilution problems. So a lot of what this video is going to be about is going to feel real similar to some of the stuff that we've done in 15.2. So don't freak out too much. But you'll probably want a calculator. You may want periodic table, maybe. Yeah, probably for this particular little video, because there's a couple little practice problems in here, not too bad. All right, let's move along here. So standard solutions. Standard solutions are, simply put, pretty commonly used solutions that we use all the time in chem labs. A lot of times when we have chemicals that we have to use in the lab, we either have to make them up ourselves or we're diluting them from something. So it just depends on what we need to do. But the important part about a standard solution is that it has to be made very precisely. When you're doing any sort of analytic chemistry where you're trying to get quantities. You want to make sure that the solutions you're using actually are 0.1 molar and not just kind of sort of approximately 0.1 molar or whatever. So there's a list of kind of some of those commonly used solution concentrations down there. 0.1 is the one that I use a lot in lab here, but sometimes 1.0 molar as well. We can use either solids or liquids when we're making standard solutions. Just depends. Technique's a little bit different, and I'll show you both of those here in this video. But the one piece of equipment that's different is this thing down in the bottom right. It's called a volumetric flask. It's a very specific type of volume measuring device. Regular beakers that we use, or graduated cylinders, aren't quite as precise as this. Beakers definitely not precise. They're best for approximate only. Graduated cylinders are a little better. We can use those for measuring, but a volumetric flask is by far the best for making a known quantity of a very specific strength of a particular solution. So here's how we do it. If you need to do something specific, like you'll get those questions, you need 500 milliliters of a 0.1 molar blah, blah, blah solution of some sort. You're going to use your molarity equation first, just like we talked about previously. Rearrange it to calculate the number of moles of solute needed, and then you're going to use molar mass to convert from that moles of solute to the mass of solute. Then what you do is you dump that solid into the bottom of your volumetric flask, pretty straightforward, and add, and this is kind of the tricky bit, just enough distilled water, maybe half of what your total value is, to dissolve it. Swirl it. Make sure to swirl with your pinkies extended. Important swirling technique is very important. But swirl it to make sure you get everything dissolved. Add a little heat if necessary, but usually not. And then the last part is that you bring the volume up to exactly the right level. There's always a calibration mark, and you can kind of see it here. I'm kind of circling it on the diagram. There's a little spot, a calibration mark, on the neck of a volumetric flask, and that tells you precisely 500 milliliters or 250 milliliters or 1,000 milliliters, whatever it is. So you've had this much water down here, you bring it right up to that exact level, and you look really closely. Remember, we've talked about the meniscus before, but you want the bottom of that curve of the meniscus to be right at that graduation mark. And then you know you've got exactly the right quantity of exactly the right concentration. Here's an example of one of those type of problems that you'd have to do for this. This is a lot like the solution prep problems that we talked about in the earlier section. However, what I want you to focus on when you're answering this, and I may have you do this as an essay on the test, hint, hint, that you want to write this out more of the what are the instructions for preparing this? Can you describe how to use this volumetric flask method to produce the type of solution? So you're going to be preparing 1.5 liters of a 0.2 molar potassium permanganate solution. So you probably need a calculator, periodic table. Probably you don't remember what permanganate is, so you might need to go look up what the name of that, what that formula of that ion is. So anyway, hit pause, grab yourself some scratch paper, solve it out, and then we'll take a look at what the answer is. Here you go. Okay, so here is your solution. How do you prepare 1.5 liters of a 0.2 molar potassium permanganate solution? Well, first is the math part. You got to figure out what potassium permanganate actually is. The formula for that is KMnO4. MnO4 1 minus is permanganate, so that's why there's one potassium that goes along with that. Hopefully you got that one right. Then you use your molarity equation to kind of solve for the number of moles of potassium permanganate you need. So here is our molarity solution. Molarity equation is right there. Here it is rearranged to solve for moles. So that's why I plugged in my numbers. 0.2 molar times 1.5 liter gives me 0.3 moles of KMnO4 is what I need. Next thing is use molar mass to figure out what number of grams you need. This 158.04 right here is the molar mass of potassium permanganate. Again, that comes from the mass of 1 potassium, 1 manganese, and 4 oxygens. So you have to go look up what that is and add them all together. But you should get 158.04. You multiply it by your number of moles, which is 0.3, and you get an answer of 47.412 grams of potassium permanganate. We only have, looks like, 2 sig figs, so it would actually be 47 grams. So this last part's the description part. Hopefully this is kind of the essay question part of this. You'd put your 47 grams of potassium manganate in the empty 1.5 liter volumetric flask. You add just enough water to dissolve it, maybe half of that 1.5 liters, somewhere in that range. And then you'd add just enough water to bring the total volume up to 1.5 liters. Then you know you have exactly 1.5 liters of solution, not 1.5 liters of water. 47 grams of potassium permanganate takes up space. So if you have 47 grams of KMnO4 and 1.5 liters of water, your final solution volume is going to be too big, and your standard solution won't be quite right. It'll be a little bit off. So there you go, how to do standard solutions with solids. Doing it with liquids is pretty similar, except that this is actually more of a dilution problem. It's kind of the same idea, but now you're not putting a powdered solid in the bottom, you're putting a liquid of known concentration, like acids come in already pre-concentrated values, and we need to make a standard solution out of it. So here's what we use right here, and it's in this bright red. It's our dilution equation. M1V1 equals M2V2. Pretty straightforward, easy to remember. M1V1, the molarity of the first equation, or first solution times the volume of the first solution, has to equal the molarity of the second solution times the volume of the second solution. So again, fairly simple little formula right there. I'll explain how that works kind of in the next slide a little bit. But what you would do is pour about half of your distilled water into the volumetric flask. Then you would add your concentrated solution, and I'll explain why in the next bit. And then you're going to bring the water level up, just kind of like in the other one, up to that needed volume. One of the key things that I want you to recall from this is that you always put the water in first. This is the big difference. Water in first, and then you add your concentrated acid or your concentrated solution to it, not vice versa. Here's why. Turns out, when you add concentrated acid to water, it's an extremely exothermic reaction depending on the strength of the acid that you're adding. For example, when I do this in lab, sometimes I actually have to do this in an ice bath or a cold water bath. So much heat is generated that the solution can boil, it could potentially even crack the beakers, which, as you can imagine, boiling acid is kind of a bad idea in terms of, life. So when you're doing this, it's really important to make sure you've got the acid in there first. The reason why, sorry, I just said that totally wrong. Have the water in there first. Don't listen to what I just said. If you've got water in there and you add a couple of drops of really concentrated acid, it's going to get really hot. It may splatter, but most of what you're splattering there is hot water. Think about what happens if you do the opposite. If you've got a ton of concentrated acid in there and you put just a little bit of water in there, again, it's going to get so hot that that water is going to boil. But now when it splatters, it's going to be splattering concentrated acid everywhere. Incredibly unpleasant circumstance to have splattering, boiling hot, concentrated acid all over the place. You can imagine that's definitely not something that's fun. In fact, this is such a common thing. Say, add acid to water, add acid to water. It's such a common thing that chemistry students have as a mantra that it's actually spawned a whole bunch of chemistry humor. I know chemistry are bad humor, but I found these in a quick search. It's pretty fun. My favorite is the Dos Equis guys over here. But in any case, it's just one of those things that I want you to kind of keep in mind, that if you ever come across this, that you want to have water in that vial first, then you add acid, and then you bring the water up to the final concentration. That's the key that I need you to know about this. So here you go. Sample problem in terms of dealing with dilution. Again, you're going to use our dilution equation. Your dilution equation is based on molarity. It's really not that challenging. Basically, if you think about this equation right here, that's the rearrangement of your molarity equation. M1V1 equals moles of solute in your first solution. It doesn't matter whether that first solution is the dilute one or the concentrated one, but whatever you're picturing as being your first solution. So when you're adding water to a concentrated solution, you're really not changing the number of moles solute that are present. You're just adding water to it. Whenever you bring that volume up, whatever number of moles is in there, whether it was 2 or 0.5 or 0.7, it's still there. You're just adding more water to it to make it more dilute. So that means that whatever your moles of solute are at the end has to be the same as whatever your moles of solute were at the beginning. So if this is your beginning moles of solute, then here's your end moles of solute, right? Well, and in your end moles of solute, in your final solution is M2V2. So this is where we get the M1V1 equals M2V2 equation. If that didn't make sense to you, don't worry about it a whole lot. If you can use the dilution equation, you're in pretty good shape, okay? M1V1 equals M2V2. So here's your sample problem. Hit pause after you're done reading this one. Again, you might need a periodic table and a calculator to go answer this one. But what's the amount of stock acetic acid solution that you would be needing to make 500 milliliters of a 1.00 molar acetic acid solution? So stock acetic acid is 17 molar, incredibly strong, not your household vinegar like you're used to. And the formula for it is HCH3 COO, Chiku. All right, hit pause, solve it, come on back. There you go. Here's your solution to this problem. Here's my dilution equation, M1V1, M2V2. By the way, it does not matter which side is dilute and which side is concentrated. It'll solve the same way as long as you have, and this is the key point, the molarity and the volume of the same solution. So if you decide that this over here on the left, your M1, is your dilute solution, then make sure that this volume is of the dilute solution. If this M2 over here is your concentrated, then make sure that your V2 is your concentrated. That's the key point here, and that's where I see students make their mistakes. So again, here you can see I've plugged in the numbers. Here is my dilute solution, what I need, 1.00 molar, 0.5 liters. Again, don't forget to put it in liters. And then the other side, here's my concentrated solution, and I don't know how much of that I need. So that's what I'm solving for, and you end up with 0.0294 liters. It's actually 29.4 milliliters, and this makes sense. You should have, in a dilution problem, your final volume should be quite a bit smaller than your original volume. If you're trying to make a dilute solution, you really should only need a few drops of concentrated solution to make that dilute solution. So if you're getting an answer that's bigger than your original volume, you've done something wrong, and check your algebra. All right, there you have it. Pretty straightforward. Main ideas from today, that when you're producing standard solutions, you need some specialized equipment called a volumetric flask. You need some careful technique as well, that you want to make sure that you're adding only enough water to dilute, and then you're bringing the water up to the final volume to make sure that you have exactly the right volume of solution, not a particular volume of water that you're looking for. You're going to use molar mass in the molarity equation. This whole chapter seems to be about the molarity equation. But when you're creating solutions from solids, that's kind of where you start. When you're using creating standard solutions from liquids, you're going to be using the dilution equation, M1V1 equals M2V2. Make sure that when you're diluting strong acids or strong bases for that matter, same rules apply, that you're always adding acid to water, not the opposite way around. And then if you're looking for a 4, do some background research. Why is it that diluting acids or bases is such an exothermic reaction? What's going on? And identify which acids would get the hottest as a result of what you did. So there you've got it. 15.3, dilution, standard solutions. See you in class tomorrow.